Shushanji, you may try sharing your slide.
Sure.
We'll just check if everything is working. So good evening, everyone. Like while Professor Shushant Kumar is trying to load the slide, let me take this as an opportunity to introduce him. Currently, he is the head of Department of Chemical and Biochemical Engineering at IIT Patna. He hails from this very state. He did his BS in chemical technology from Institute of Chemical Technology. It's quite likely that one of the participants could be from that place. So he went on to do his PhD from Florida International University and postdoctoral work from Okinawa Institute of Science and Technology. So he has been with us since August 2016 at IIT Patna. And today he's going to talk about his work on carbon sequestration and conversion to fuels. So Professor Kumar also has a patent on method and system for sequestering carbon dioxide and producing hydrogen gas. This was way back in 2012, and the patent has tremendous potential for application given recent developments and the parity in terms of parity tilting in terms of hydrogen fuel becoming more and more popular. So, Professor Kumar, over to you. Yeah.
Thank you so much, sir. Good evening to everyone. I hope my slides are visible and I'm audible as well. Is that fine?
Yes, your
Hello.
slide is visible in full screen mode and your audio is good.
Okay. Okay. Well,
Thank
thank you
you.
so much. Thank you for the invitation and also for the nice introduction. So as you may see that this talk, which I'm going to deliver today, is about the catalyzing a sustainable future and the use of sunlight for the conversion of CO2 to fuels. So in this one, I have compiled 4-5 works of ours from our lab, and I'm going to give an introduction of how tricky and how challenging this reaction would become when we use the sunlight for the conversion purpose. So beginning with the fuels, the present situation in which we are in, if we see the graph over here, we can see that the CO2 has a vast emission from the different sectors, right from the energy, road transport, industry, everywhere. From every means, we are burning the fuel, and in turns, what we get is a lot of CO2. And this is the graph where you can see that the million metric tons are emitted every years, and it is keep on growing with a projection that it will reach to a condition when the situation would not be so nice and so ideal to live. Now, there have been efforts, as all of us know, that how to mitigate CO2. And to do that, people have been trying the post-combustion, pre-combustion, oxy-combustion, and then there have been their own disadvantages, saying that all those possible approaches require a lot of energy input, and those energy would come from the burning the fossil fuels. So if you do a simple calculation, you will see that for every energy that we are putting in, the total amount, the net value of CO2 that we are capturing is quite low. So what could be the possible ways? The possible way that could be not to capture the CO2, rather convert it into some fuels. And the way we can use that is using some renewable sources. And one of the renewable sources is the sunlight. As we all know that the sunlight has energy in it, and those energy are in the form of the UV visible and the infrared. And if we look at the spectrum of the sunlight, what we see that the UV light is just 5%, mere 5%, and the visible light is about 45%, and the infrared is more of 50%. And the band gap or the energy that it has is quite high for the UV, and the visible light would be lesser, and infrared would be the least. So this is just the introduction of showing you that there is a need of using the renewable energy sources and combining them to convert the CO2 into fuels. So to do that, there have been uh, approach which we call as the electrochemical CO2 conversion. And electrochemical CO2 conversion, though give a good efficiency compared to other techniques, but it has its own demerit that it uses electricity. Now, if we try to see here what is shown in this plot, we can see that this is a flue gas capture. There is a home and transportation. Everything is giving you CO2, and then we use the renewables and the water to convert it into the chemical feedstocks and the fuels, and then it goes back to the long-term energy storage, which provides the energy to the home and also to the industrial and power emissions. So combining these things, what we see is that we are trying to complete the carbon cycles, which would not try to stop the CO2. It will try to control the CO2 level, whatever we have right now. Now in our lab, what we are trying to do is not through the electrochemical way, but to do with the photocatalyst, where there will be no electricity. So the total energy input would be nothing. We have to just use the CO2, water, sunlight, and a good semiconductor. Now, the whole talk which I will be delivering today is all about understanding the semiconductor, its use, and engineering those semiconductors in a way that it could be giving us the CO2 to some fuels, and then to understand the mechanism of how those semiconductors or those photocatalysts uh, could be could be used or for the scaling up of those reactions. So if we see, this is one of the summary of how to look up when we have to really scale up. This is a solar refinery which people have been speculating that if the reaction efficiency becomes higher and higher in the coming time, because this research is still at its nascent stage, and if there will be CO2 and H2O activation, because all of us know that the CO2 is a very neutral molecule which requires activation, and those activation could be taken place when we have some extra energy from somewhere. So those can be supplied from thermolysis, thermochemical, catalytic, photoelectrochemical, photocatalytic, or photolysis. And those can give us CO, CO2, H2, and H2O, and also the oxygen, the other half of the reaction. And those can be used for the catalytic conversion for water gas shift reaction, the reverse water gas shift reaction, methanol synthesis, Fischer-Tropsch, and everything would give us the fuels. And then these approaches could be seen as a possible and the next generation reaction, which has potential to be upscaled and which has the potential to be used in a way that gives us less energy expenses for the conversion of the CO2. Now, to get into the research that I do, let me show you one reaction which is CO2 plus H2O giving us methane, and then this you see delta G is 818.3 kilojoule per mole. And then the another reaction, which is nitrogen. So nitrogen, the reason why I put the nitrogen, because it has equally the same kind of a concept of having a large energy input that is required for the conversion for the synthesis of ammonia, because all of us know about the Haber-Bosch process. So my lab at IIT Patna, we are working both in the conversion of the CO2 and the formation of the ammonia through the renewable ways or another less energy expensive ways that we are trying to target. Now, both of these reaction are very are non-spontaneous, because the delta G, if you see, so thermodynamic does not allow us to really perform this experiment. Now, if you how we do and what is the basic concept of how one can really perform this reaction, that's what we are going to see right now. What we do, we prepare a photocatalyst thin film, which you can see here. Then we irradiate, we pass the CO2 and H2O in a gaseous form. Then we irradiate with a simulated sunlight that we have. Then on the surface, we have the electron and holes, which participate in the reactions, which you can see here. There are reduction reactions, there are oxidation reactions, and those are giving us methane, CO, ammonia, as well as the oxygen. So those reactions takes place on the surface. So whole reaction is actually a surface phenomena that happens on the surface. But if you look here at the course of the reaction, the CO2, N2, and water has to go to CO and methane, and then also form hydrogen and ammonium ion. Both of these are at a higher energy level than the CO2 and CO. As I have shown here, that these are non-spontaneous reactions. So how to achieve those? So those are achieved using the photons that we are supplying through the sunlight, and those extra energy which is given there would going to get this reaction going, and hence we are going to see how these reactions are happening, and how using the different catalysts we are going to choose this different selectivity towards the different products that can be possible. Now the another thing that you can see is the oxygen is there, because let me give you one input that the when there is a competition between CO2 and H2O reactions, or nitrogen and H2O reactions, there is always a preference for H2O to get converted to hydrogen as well as oxygen. So hydrogen water splitting is much more preferable than converting the CO2 to some other compounds like CO or methane or some other thing. And now the second thing that you can observe, that I'm always talking about the gaseous phase. I'm not going into the liquid phase for the CO2 reactions. The reason is, like when we were doing the experiments, we keenly observed that when we were preparing or synthesizing the catalyst and performing the experiments, we observed in the liquid phase that there were some products like acetic acid or some other hydrocarbons, which could result on not from the reactions but from the other ways or the synthesis process, and that could be erroneously misinterpreted as the product. So to rectify those things and to understand these kind of reactions, we prefer to work in the gaseous phase reactions. So now, when I was talking about the surface phenomena of this reaction, I told you that there is a lot of drama that goes inside the catalyst. And when we look inside, what is this? This is a surface recombination. So to explain this surface recombination, what has to be understood is that within the catalyst, there are places, there are certain sites at which the electron and hole recombine and they are lost. Since they don't get to reach to the surface of the semiconductor or the photocatalyst, they don't interact, they don't react, and they don't participate in the reaction. So although we are supplying a lot of intensity of the energy, or there are very low band gap of the semiconductor, that is not going to give us a lot of product. The reason is because there are a lot of instances where the recombination events happening, that is the electrons and holes are recombining, and then they are the more of a liberation of the heat. So basically, when we combine all this basic understanding, what we see is that to convert the CO2 into some product, we need to be in the gaseous phase. We need to have a semiconductor that should be operational in the visible light regime, the 400 to 700 nanometer. And besides that, there is another point, that if you have to be selective towards the product that CO is giving to methane, or the carbon dioxide is going to CO, or carbon dioxide is giving to methane, you have to have that much of potentials. And those potentials are telling you are actually are referred by the thermodynamics, because thermodynamics tell you that whether those kind of the products could be possible or not. And those thermodynamics are coming actually from the kind of semiconductors that you have prepared, or the kind of the photocatalyst that you have prepared. So the band positions, the conduction band position and the valence band position, those are going to also govern how much of the CO2 to CO, not how much, whether it is feasible for the CO2 to convert to CO or methane or some other product. Now, besides those thermodynamic aspects, there are also a kinetic aspect, because these reactions are very sluggish, and because of the lot of hindrances, the product that we are getting right now is not to the very high kind of a product, and that has both of those limitations which I told you, the reactor design as well as the kinetics that one could have. And it's a global issue that is prevalent. But the good point is that these reactions are feasible, and one can really convert the CO2 with the in the presence of sunlight to some fuel which can be used. Now, here, first work is about copper and sulfur doped in the graphitic carbon nitride. So, graphitic carbon nitride is a 2D material which has a very nice band gap. Which nice, I mean, it's the band gap of graphitic carbon nitride is 2.7 eV, which falls within the visible light. So that satisfies one of the criteria that we have. Now, what we did using the synthesis method, we have doped the sulfur by calcining by doing the calcination of thiourea, and graphitic carbon nitride is prepared by calcining the melamine at 500 degrees Celsius for both for 4 hours. And then we have the copper, which we have in doped in the photocatalyst that we have prepared. And these are the XRD pattern, where you can see that the planes corresponding to 002 and 100 are prevalent in these kind of photocatalyst. And if we I'm not able to show you here, but if you can see that there is a the intensity of these peaks have weakened, and also there is a shift of 002 plate towards the higher angle. That means there is a reduction in the interplanar spacings of the graphitic carbon nitride. And the second peak, which is shown here 100, that shifted towards the lower angle when we have 2% of copper in SCN. SCN refers to the sulfur doped graphitic carbon nitride. And that means that there is an increase in the void to void distances where the sulfur and copper are doped on the in the plane, and they are residing in the plane of the graphitic carbon nitride. So we can assume what we see here, that the graphitic carbon nitride, which was initially have a 2D structure, the interplanar spacings has reduced, and also the copper and sulfur has been on the surface of these has has been in the plane of the graphitic carbon nitride. So this is the structure which has been in line with the HRTEM images that we have seen. You can see that there are these planar kind of a structure we have got for the copper SCN and SCN. This has been there. Now, besides these facts, we went to do the optical and electronic properties. Here you can see that the band gap here, this plot is for the UV visible DRS. The band gap has not changed drastically. What has changed is this effect. What is this effect? This effect is about the plasmonic. So copper in general shows the plasmonic effect, and that helps in activating the photocatalyst to produce more of the product, or to have more of the electron onto the surface, which helps in which helps in more product formation. Now here you see this is a photoluminescence intensity. So as I told you, the reason of the recombination, that the electron and hole recombines and they are lost. Now here if we see, the more intense peak would refer to that there are more such events, and hence more intense peak is not good for us. We need to have a very low intense peak, which would tell that the electron and holes are reaching to the surface relatively more when we have a higher intense peak. So this was true when we have graphitic carbon nitride. So graphitic carbon nitride is the function of a graphitic carbon nitride is limited by the recombination events. However, when we have 2% or 3% of the copper, we have seen that such recombination events have reduced, have fallen drastically, and we don't see such. We expect the electrons and holes to be more on the surface, although both of them have the same kind of a band gap or similar band gap. Now, what we did, we were more excited in understanding, as I told you, that the conduction band position and the valence band position both are very much important when we are deciding the fate of the products, or the kind of the products that one should expect to see. So what we did the valence band XPS, and here you can see that the copper SCN has shown 1.55 EV, and graphitic carbon nitride has shown 1.88 EV. Now, what does it mean? That it means that once you have doped the copper and the sulfur in the graphitic carbon nitride, that has upshifted the valence band, and this is what you see here. That there is a upshift of the valence band. Initially, the graphitic carbon nitride valence band is somewhere here, and the SCN is here, and then the copper graphitic carbon nitride. If this is the band gap, this is the band gap of this photocatalyst, the conduction band has gone up. That means the reduction capacity or the reduction ability or to form the carbon dioxide to uh, carbon monoxide or methane, the thermodynamic efficiency becomes higher for copper SCN. And that is a great thing. Now we have to work for the, so thermodynamics says that yes, copper SCN is very good. Let's go for and check the kinetics. Now, in the design that we have in the reactor, what we have is that what we have seen is that the methane and carbon monoxide both have formed, and these are the product formation rate. Here you see that the 2% copper SCN has given us the highest amount of the methane, and likewise it has also given the carbon monoxide. Now we look at the total consumed electron number, and we have seen that yes, 2% copper SCN has given us more. Now we looked at the stability of these results. So we have conducted the experiments for more than 5 cycles, and here we are showing only 4. So here you can see that the consistency has been maintained for the product amount. Now, we did not pay attention to the oxidation product in this work, because we were much more excited that yes, this reaction can also happen, which is thermodynamically very tricky and kinetically very sluggish. So that happiness did not allow us to concentrate on the oxidation products, but in the latter work we pay a lot of attention to those aspects as well. Now we looked into the mechanism at which this reaction was happening. So we performed the in situ ESR with the help of IIT Bombay, and what we have seen that the graphitic carbon nitride under the light has a more intense peak than the under dark, and that is because of the free electrons that is there in the graphitic carbon nitride, which is able to react. And the same is the case of the with the SCN. But when the copper was there, we have seen that the intensity has dampened, and the reason is that it has transformed from the paramagnetic Cu2 plus to diamagnetic Cu plus, and that tells us a lot about the kind of the mechanism that we may expect in such kind of a photocatalyst, and that I will show you in the next slide. And over here we have the same kind of a story which we have seen. So what we have seen, the Cu2 plus is there, which is accepting the electrons, and then there are the free electrons which is present when we have irradiated the photocatalyst. Now, these are the in situ drifts. What we do, we pass the CO2, H2O, we irradiate, and then we look at the drift result, the IR results, and we see the new peaks that are forming. Though here you don't see a very clear differences, but when we do the second order IR derivative, we can see the spectral changes in much more detail, where the COO minus, which shows that the CO2 accept the electron from the surface of the photocatalyst and transform to COO minus. Now this COO minus becomes very active intermediate, and then it starts reacting with the H2O, and it forms different species, which is shown here. That I'm not going into the detail, but there are some reaction steps that has to happen. Now, this is a summary of the mechanism that happens in this reaction, where one more important thing that I would like to tell you, that this copper, which we have doped, as we all know that the copper is very prone to oxidation when we even keep the copper in the atmosphere, in open atmosphere, it can form an oxide layer of 3.4 nanometer in 1 month. So that's the kind of oxide cell it will form, and it will transform to Cu2O. And then what we see is that the copper no longer remains Cu0, the metallic form, which exhibits the SPR. That's what we have chosen for. It transformed to Cu plus, and also it can transform to Cu2 plus, and hence these different oxidation states can interchange in the presence of the electron and holes, and hence this could be the possible mechanism. And then what we do, we look at the Cu plus, which I told you, because of the in situ ESR results. We see that the CO2 transform to CO minus, and then this H2O gives us H plus. Oxygen should liberate, which we have not quantified in this work. And then this CO minus NH plus would give us to CO and methane. So this was one kind of a work that we have done. And then this SPR effect is there, which we don't deny. That would also be present in this kind of a photocatalyst. So this was one of the work that we have done in 2019. As you can see, this was our first work. And then what we did in different work is we were excited in knowing what is what will be the effect when we have a PN heterojunction, because we know that we have to somehow separate these electrons and holes so that the recombination would not happen and we can get more electrons on the surface. And to do that, we should be able to control or the tailor the photocatalyst in a way that it should not recombine too much. So to do that, we have used the Cu2O, and first we have prepared the SNS2 and SNO2. The reason why we use this SNO2 and SNS2 is that they are very much having a oxygen vacancy, which I will show you. And then the Cu2O, because we have good memories with the Cu2O, and we will show how this Cu2O is going to govern all the reactions and giving us more reduction product when we are going to have a SNS2 and SNS2, SNO2, and CO2. So here you can see a very flower kind of structure for SNS2 and SNO2, and also for the CO2, this is more like an accordion kind of a structure. Now, when we looked deep into the HR atom, and what we have seen that this has formed a heterostructure. So that has formed that was our goal to form a heterostructure using SNS2 and SNO2, and we achieved that using the hydrothermal reactor. And then when we looked into the structure, what we have seen that there has been surface oxygen vacancies, which you can see here. And these oxygen vacancies, because the reason why I'm repeatedly telling you about the oxygen vacancies, because these oxygen vacancies, there is still an argument whether these oxygen vacancies help in the reaction or it should retard the reaction. That means whether these sites uh, acts as a recombination sites, or it hosts one of the electrons or holes and let the other species, either electron or hole, to go and reach to the surface of the photocatalyst. Now, these were our characterization results, and we performed the CO2H2 gas phase reaction. We have seen again the CO, methane, and hydrogen formation. And let me tell you that CO and hydrogen can be seen as a syngas, which can be transformed into methanol. And when we checked it, what we have seen that the CO2O, SNS2, and SNO2 was giving more of a methane and less of a CO, and SNS2 and SNO2 was giving more of a oxygen, more of a carbon monoxide. So to do that, look into the mechanism. We perform some more characterizations. So starting with the PL intensity, we have seen yes, CO2O again helps in prohibiting the recombination events. And then when we look at the transient photocurrent response, which tells about the electron mobility, as expected, this photocatalyst has shown a better photocurrent when we put the light on and off, and when we as compared to SNS2. And this was the position when the light was off, and you can see that there was no current. And once again when the light was on, there has been a consistent performance in the CO2O, SNS2, and SNO2. So further, what we did, we performed the in situ ESR. Again, this has shown a higher, the dark was under dark, the signal was intense compared to under light. That means there has been a reduction of the electrons, and these oxygen vacancies might be working as the place where the electrons are captured, and it was hold at in the oxygen vacancies. And when we have added the CO2O, again there has been transformation from the paramagnetic CO2 plus to diamagnetic CO plus. And then what we did Morse-Schottky plots to see the effect of using the p-type to n-type semiconductors. And here you see this is a n-type, and this is a p-type and n-type. And when we have this kind of a heterostructure, we were keen to understand how this kind of a photocatalyst works. And here you can see this is the energy band structure. starting from the conduction band to the conduction band. So here the conduction band is of p type, and this is the n type. And then we have also seen and these were the potentials from the CO2 to CO conversion, and we have minus 0.693 for SNS2 and SNO2, and for CO2O we have minus 0.483. Now, we did perform for the nitrogen and water in the aqueous phase, and in the aqueous phase, we have seen this NH4 plus forming. And what we did, we have seen with sacrificial agent and without sacrificial agent, and the way we were measuring the quantity was Nessel's reagent, and we concluded that whenever we use a sacrificial agent, there has been an interference of these sacrificial agent in doing the precise measurement of the ammonium ions. So these were our observations, and then we tried to understand the possible mechanism. So this is a p type. The Fermi level is there will be equilibration between the Fermi levels, and one which is closer for the p type would, and then the another which is closer to the conduction band for the n type has to equilibrate, and this is the equilibrium. And because of this possible way, the electron would try to transmit from the p type to the n type, and then the reverse is happening for the holes to happen. So this could be a mechanism which we have seen for this kind of a photocatalyst. Now, there was another work that was because of an interesting fact that the MIL, which is metal organic frameworks, uh, and based on the iron. So what it has, it is this kind of a structure which you can see more like a spindle structure, and in this structure. This is more of an organic inorganic mixed, where inorganic part is FeO clusters and organic is hydrocarbons framework. And in this, we have doped the manganese and zinc. You can see that there has been a distortion of the XRD peaks, and the reason we don't know, but what we have seen is that zinc and manganese both were present, and this has been synthesized using the hydrothermal reactor, and there could be a more complex mechanism which could happen here, but that was not part of our interest as of now. First we did the optical and electronic properties. We have seen that the manganese and zinc was performing very close to each other, with the MIL was pretty low with the absorbance, and also with the performance with the electronic and optical properties. What we have seen that the manganese and zinc was neck to neck with the performance of the photocurrent, and also it was with the electron mobility, and also with the energy band structure. It was too close to get a call and to give a clear picture with the manganese and zinc, when zinc has a bit of upper hand, but it was not that far. So this conduction band position was minus 0.583 compared to minus 0.553 for the manganese. And there is an upshift for the valence band, saying that the zinc would prefer more to the reduction capacity. So here we have performed, and what we have seen is a more of a CO formation in such cases when we have the zinc. Now, when we, as I told you, that this is an organic compound, so there could be the carbon which can come from the from the photocatalyst that we have prepared, or the carbon from the carbon dioxide. So to really understand which carbon dioxide are we not considering those which are coming from the photocatalyst, we perform the in situ drift in the presence of 13 CO2, and this has shown a clear understanding about the mechanism, and a clear the presence of 13 CO minus told us clearly that yes, the reaction is feasible, the reaction is happening. The CO2 which we had, the CO2 is taking up the electrons and is forming different species which are vital, or the intermediates to form the products such as CO and methane. And then we did for the ammonium ion also, and with that we have seen that the zinc is again performing. We did the in situ drift, and we have seen the stretching vibration, and also the bending vibration. So both of those of NH were present, and then we have zoomed it to show you in a better way. And this is the This is what we have seen. Now what we did further, we did the contact angle measurement, where here you can see that the MIL 88A 52.9 degree, 77.4 degree, and zinc 36.1 degree. Now when we look into the interface, what we know is the CO2 is a neutral, and CO2 has a very low solubility in the water. So if it has low solubility in water, CO2 or nitrogen finds a very difficult time in diffusing through the water and contacting the surface of the photocatalyst. So it becomes more of a mass transfer controlled reaction, because this CO2 has to penetrate and it has to be near to the surface of the photocatalyst. And if that is happening, the electron will be taken by the CO2 and nitrogen, and then the further those reactions would happen. Now what we in another work, follow up work for this work, we did some with the help of one of our colleague, we performed some molecular dynamics simulation, and what we have seen that the CO2 molecules, when we have a hydrophilic surface, it does not stay longer for it does not penetrate easily, and it also does not stay for longer. And when we have a hydrophobic surface like the one we are seeing here, manganese, it penetrates well, it stays there for a longer time, and that helps in the photo conversion of these CO2. Now when we compare the manganese and zinc, as I told you that zinc was performing better than the manganese, then how this could happen? Like you have a hydrophobic which should have more of a CO2, and then you have a zinc which is not so hydrophobic, but it has a hydrophilic. Now what we believe that it has to have two things. One is not only hydrophobicity, or relatively hydrophobicity, or more of a angle, a water contact angle, or a three phase reaction. You have to have the very good optical and electronic properties to combine with, so that it can give you more of a product. Now that is happening only with the zinc and not with the manganese. Manganese was very close, but it was not that to be a winner. So then we summarize our work, and we see that the transition metal can there have been XPS work which I have not shown here. There are a lot of other supplementary work which I have not shown to be within the time. But what we think that the electron transfer from oxide ion to Fe3 plus to form Fe2 plus under the visible light irradiation, and this at this Fe2 plus, the reaction is happening to of the CO2 and nitrogen. Now, in the final work, which I'm going to show you now, is silver decorated over the zinc oxide and the beta polymorph of gallium oxide. Gallium oxide is a very high wide band gap, which requires a lot of energy. Now, why we are interested in? As I told you earlier, that since we have to have a favorable conduction band position and the valence band position, so we have to have, once we have a very high wide band gap, that means we have a large thermodynamic or driving force for the reaction to happen. Now that is being provided by the gallium oxide. Now to bring it down, one can use the zinc oxide and then use the plasmonic effect of the silver. And hence this was the basic concept that we have behind designing this photocatalyst. And these are the catalyst synthesis steps, which you can see. These are the XRD pattern, which clearly show the presence of silver, and the gallium zinc structure, that heterostructure that we have. And these are the HR10, where we can see the different interface of the silver and the zinc oxide to give you an impression. Now, in the UV-vis DRS, you can see the increase in the absorbance, which is primarily because of the presence of the silver, and this is also, there is a shift in the absorbance spectra. This shift is all because of the drop in the band gap values, and which we will see in the next slide, that how those drops and would help, and those we were going to consider. Now, when we have transient photocurrent response, we see that when the light was on, The silver one was giving a highest compared to the zinc, as well as the other photocatalyst. The lowest was the gallium oxide, because of the reason why, because the electrons are not generated too many, and also there have been recombination effects. So then this is the band structure, energy band structure, which you can see with the different one. Silver has a high position for the conduction band, and compared to the gallium, which was quite low. So what we did with this, we tried to upshift and lower the band gap. So here the band gap was just 3 ev compared to 4.5 ev of gallium oxide, and also the conduction band was more than 0.53 volt, and hence it was able to give us CO2 to CO. Now here you see, this is the yield percentage for the methane, CO, and H2, and it was silver, which was giving a lot, and then this was the ammonium ion, which we did, and we also characterized the in situ drifts with the 15 nitrogen, and you can see that those reactions are possible, and we can see the 15 NH3, 15 NH4 plus, those are present. We have seen the bending vibration, we have seen the stretching vibration. This is for stretching vibration, this is for bending vibration. So those species were present in the spent catalyst that we have. And now what I want to show you is this video. I'm not sure whether this can run right now or not, but this is the video that I would like to play, where water contact angle between the gallium oxide and the yeah. So, and the silver gallium oxide, gallium zinc, you can see. So gallium is hydrophilic, and this is for the silver. You see the difference? This becomes more hydrophobic, and because of its hydrophobicity, which I have discussed earlier, this is, and also combined with the optical and electronic properties, this was giving a more of a CO and hydrogen. And now we are in the process of redesigning the reactor, so that we can have some because of these studies, we have some understanding about how to really come up with more of a yield, so that it can be economically viable, or one can really think of upscaling such reactions. But yes, these reactions, as I told you, that these reactions are first of its kind, to convert CO2 to fuel, without the use of any energy input. No energy is involved, only the sunlight, or simulated sunlight that we have, and just the photocatalyst. So thank you so much. I will be very happy to uh, take some questions.
Yeah, okay. Thank you so much, Mr. Kumar. So, are there questions? So, okay, like seems participants are feeling hesitant to ask questions. So, I would like to ask, means I have a curiosity here
Yeah,
that
sure.
suppose when we are going for carbon sequestration and conversion of it into a fuel, right, through a kind of through a reaction. So, what are the energy odds? So with the current state of the art, is it energetically a favorable process or we really pump in energy?
We have to as told, there are reactions which uses the CO2 to transform to some fuels, but all of those are thermocatalytic, like they use the temperature as a driving force and the catalyst to run such reactions. But here what we are doing, we are using the photocatalyst and the sunlight, which is free to really
Hmm.
perform such reactions. And also we are not using hydrogen. Here you can see that we are using the water, which is in plenty. So CO2, which is a waste for
Hmm.
many industries, and H2O, which is not so relatively free, but can be. And then CO2 and H2O would give us the kind of the fuel that in the form of methanol or methane or syngas we can form.
Okay, and so these yields are reasonably high.
It's are in par at par with whatever the global reports are. We are not any less, but yes, this is the nature of this reaction that needs to be overcome by through redesigning the kind of the reactors, or through designing more of a perfect photocatalyst.
No, preparing this photocatalyst itself uh, is a process which demands energy, right?
Yes,
So my question was more pointed towards that. I completely agree. Once the photocatalyst is available, then you can use sunlight and go ahead, depend completely on it. Or alternatively, like temperature gradients, like during nighttime, temperature gradients to run some of these processes. So however, like when we look at the amount of photocatalyst required and the amount of energy which goes into it. So the current state of the art is already showing promise, you mean?
yes, there are some promises because this work is at its
Mhm.
nascent stage. Like people
Mhm.
in the last 4 or 5 years, they have started uh,
Mhm.
to do such
No, so this will
reactions.
have one of the then potential areas where we can tap sunlight,
Correct.
right? Because photovoltaics has its own set of issues related to waste management.
Yes. Yes.
Okay, thank you so much,
Thank
Mr.
you, sir.
Kumar.
Thank
So
you.
any further questions from the audience members? Fine, if there are no further questions, let us thank the speaker.
Thank you.
Thank you so much.
Thank you, sir.
Thank you. So to the FDP participants, there is a timed, uh, basically a form which they have to fill right now. This is kind of an evaluation test, if you say. So you may start now, right away. So these are simple questions based on the talks or the discussions that we had over last uh, 2 weeks. And I would expect all the FTP participants to fill it. Internal candidates, you are not required to fill it. Okay, so participants. So you can go ahead, and once you are done, you can let me know so that we can close this session. So another thing, Dr. Carr had a hospital appointment. So I think he means he may leave. Actually, yeah, you wrote to me.
No, no,
I
I'm
responded,
here.
but I
I'm
still.
leaving, Ajuji. I'm leaving.
Okay,
Please.
okay, okay, okay. Thank you.
Thank you.
I also just now had my blender today. So breakfast, lunch and dinner all together. I just
Oh, I
started.
see.
I call such a meal as a blunder.
Okay. Okay, fine. Thank you.
Yeah, thank you. So we'll wait for the participants to complete the evaluation sheet, and then we'll close this session.
Okay.